All right. So, good afternoon and welcome to our webinar, Why is Greenland So Important? I'm Jerome Neufeld and I'm a professor of Earth and Planetary Fluid Dynamics, based both in the Department of Earth Sciences and the Department of Applied Mathematics and Theoretical Physics, and at the Institute for Energy and Environmental Flows. My research combines mathematical modeling, laboratory experiments, and the attempt to interpret field data to understand the behavior of the Earth and other planetary bodies. And I've studied things as diverse as the geological storage of carbon dioxide, formation and early history of the moon, and the formation of ice in the Arctic Ocean and the lubrication of the world's large ice sheets by meltwater. But today, we're going to explore why Greenland sits at the front line of global change and why it has become such a vital natural laboratory for scientific research. Greenland has been thrust into the public consciousness and the news cycle of the land. And it's a rich place, a rich land with a people who have a rich history and culture, and on which sits one of the world's largest reservoirs of fresh water in the form of one of the world's largest ice sheets. All of these things are important to understanding the background of its current political context. And so from the rapid loss of ice to the implication for global sea level, to the geological record preserved beneath the ice and the lived experience of Arctic communities, we're going to talk to some of the people in Cambridge who are at the cutting edge of research on Greenland. And they're going to offer us some insights into the processes shaping our planet's future. So with really great joy, we're joined by three outstanding speakers. We have Professor Michael Bravo from the Scott Polar Research Institute. Michael leads the Living Cryosphere Lab, which works to understand how societies live in relationship to the planet's cryosphere. And he's worked deeply with the peoples of the Arctic to understand their culture, their history, their relationship to the land, and their relationship and influence around the globe. We're also joined by Dr. Kelly Hogan from the British Antarctic Survey, which is also based here in Cambridge. Kelly is a marine geophysicist specializing in the history of the Arctic and Antarctic ice sheets and how they've sculpted and shaped the Earth's surface. She's helped understand how ice sheets have responded to past climate change and is at the forefront of monitoring how they're responding to human-induced climate change right now. And we also have Professor Owen Weller-Gibbs from the Department of Earth Sciences. Owen is a metamorphic petrologist, which means that he is adept at reading from the rocks on the Earth's surface the span of their history, from their formation to their heating and compression to how they've been deformed, which all helps us understand how, where, and why critical minerals are located on the Earth's surface today. So each of these speakers are going to share their understanding and their research on Greenland, helping us to understand the Earth's climate system, its resources, and the human dimensions of environmental change, and why this work matters far beyond the Arctic. So a bit of housekeeping. After all the talks, there will be time for questions. So please, you'll have a button at the bottom of your screen. You can submit your questions and we'll address as many as possible. And the session is both being live broadcast to YouTube and recorded, and a link will be shared afterwards for that recording. So if you have any technical difficulties, don't worry, you'll be able to access the recording later. So with that in mind, it's a critical time for polar science, for understanding Greenland and its context in world events. And so I'm going to pass over to our first speaker, Professor Michael Bravo from the Scott Polar Research Institute. Over to you, Michael.
Jerome, thank you for your lovely introduction. Honestly, it's a pleasure to be here today with so many alumni and with my colleagues on this panel. So first of all, just a quick shout out to the School of Physical Sciences for organizing this, doing it together. Also to my Department of Geography, my great colleagues in Human Geography and Physical Geography, or Professor Emma Maudsley, who leads the department. At the Scott Polar Research Institute, we are engaged with Greenland and other parts of the Arctic. I want to use this kind of short time, 10 minutes, 12 minutes, to try and entertain, but do a quick kind of overview of something to do with Greenland. What do you need to know about Greenland to get started? So if I think about what alumni tend to read, most of us see in the newspaper quite a lot of contemporary material. But what tends to be missing from that is the history of Greenland, where it comes from, the culture, and therefore the question, who speaks for Greenland, is pretty central. At the Polar Institute, the Living Cryosphere Lab does a lot of work thinking about how societies like Greenlanders live today and their history, as does my colleague, Professor Richard Powell, our SPRI director, who has led a recent £1 million European Research Council project on the material culture of Northern people. So 4 themes I want to get across today. The first one is about how we do research with Greenland rather than on Greenland. When I got the invitation to speak, it took me back to when I was last in Greenland, which you can see on the slide in November, for a conference on Greenland Science Week. And you can see, is it beautiful to be in Greenland? Yes, it is. Though there was some consternation actually at the time, because you can see there wasn't a whole lot of snow for late October, early November. What's the significance of that? I defer to my colleagues on the panel, but certainly Greenlanders are thinking a lot about the climate today. So at this conference, with the appropriate topical title, All Eyes on Greenland, I thought a really relevant question is how we listen, how we actively listen to people in Greenland to understand what they're thinking and what they are saying. That was the subject of my keynote to open the conference for the week. So the thrust of it is to say that there's a motto in Greenland, which is to say, do research with us, nothing about us without us. And for, many of you work in innovation and R&D, so you'll know that real research and breakthroughs come as the result of collaboration and partnerships. And the same is true in Arctic research with Greenland today. Okay, so that's the first kind of theme. And it's a bit of a shout out today also for Cambridge. So we're very pleased that people who've worked with us at the Polar Institute are in positions all over the world, including the rector of Greenland University, Lise Matusarvik, Marie Kleist, quite recently was working at Cambridge, and even slightly to the west in Nunavut Arctic College, the Higher Education Institute of the Inuit of Nunavut. The president is one of our alumni, Jackie Price. Now, how does research work through international partnerships? The Arctic is unusual. And here you see a meeting of the key people at this conference in Arctic research in Greenland. So international partnerships are the key. What I'm trying to do here is draw attention to the fact that the Arctic is it's a regional constituency in its own right. It's active, it has institutions, it does science, without, in the first place, kind of needing to be an extension of science or of institutions and everywhere else in the world. So there's a meeting of partners, if you like. Okay, and you see here representatives of the senior official of the Arctic Council, and at the moment, Greenland is in the chair, which rotates every 2 years. So they're in an important position for agenda setting, and this is their message: come and do science with us. What I appreciated about this conference so much was the high quality and capacity of Greenlanders to do research on many topics, some of which you'll hear about today, to do with geology, to do with the ice sheet, but also to do with health, maternity care, epidemiology, all manner of different topics. Okay. So Greenland, just to make it clear that things didn't happen in Greenland yesterday. Look, it's a tiny population, 58,000 people, roughly, who are mainly Greenlandic, and they speak Kalaallisut as their first language. Yeah? So for a start, let's remember that English isn't the first language there, that there are Arctic languages. I'll come back to that. And then, because this has to be in broad brushstrokes today, there's been a long period of colonization, particularly going back to about the 1720s, 1730s, with the Lutheran missionary Hans Eel, as the Danes call him, Hansigede, and the establishment of a Danish monopoly over fisheries, over trade in Greenland. Okay. one of the products of, I guess, Greenlandic migration into, or the migration of people into Greenland as early as 4,500 years ago. Okay, that's a long time ago, isn't it? Contemporary with the Minoan civilization in Crete. That's how far back one wants to think to get a sense of Greenland. And so we have this kind of period of colonization recently, as the 18th century, industrialization, or at least industrial technologies like the printing press, and then it becomes part of the Kingdom of Denmark officially in 1953. Against that is a tension, which is one of devolution, taking back power. The thrust of it is these people want to be able to be in charge of their own lives and have a say over their destiny. And all around the Arctic, you see this tension, because since the 1500s, we've had waves of economic expansion up into the Arctic that, boom and bust into the Arctic, and then they recede. And with that, of course, comes the power of governments and states further south, in and back. So there's a kind of push-pull dynamic that helps you to think about the Arctic as a whole and Greenland. Okay? So I wanted to put across just the sheer diversity. And this map actually does that quite well. Look at all the different languages around the Arctic and the different people or ethnicities. Just take a moment to take stock of that. That's produced again by the Arctic Council, this map. So 3 or 4 features to point out. 1, the linguistic richness. Yep. Also, Greenland is an island, clearly, but in a way, it's part of an archipelago. Look just above it and to the left, and you see in Nunavut, northern Canada, all these islands. So the way in which Greenland, it's a coastal society, is connected to its neighbors, is as a set of islands, often where the connection is actually the sea ice. Traditionally, people would travel over the sea ice, following trails to get from one place to the next. Okay. And hence, being coastal people, they were often called people of the seal, or other kinds of fisheries and marine mammals, so they were traditionally having a marine economy. Okay. And with that, if we want to understand how people are related, actually the Inuit in kind of dark blue go all the way from Alaska, where it says Inupiaq. In fact, there are even some Inuit in Siberia, just beyond the Alaska, all the way around across what's today northern Canada into Greenland. And if you look at the blue stripes in Greenland, you see it goes right from the northwest of Greenland is one section, another section, the west of Greenland, and then another on the east. So we see here actually that even within Greenland, there's diversity. There are subregions within Greenland. Okay. As a research project that was funded for 3 years, focused more to the west of Greenland, but nevertheless, it's interesting. We wanted to reimagine what the top of the Americas looked like. And the question that I had with my colleague Claudia Porta, anthropologist from Argentina, was, do the trails of the Inuit over the sea ice, do they meet up? So we worked with elders and hunters, as well as in libraries, to put together all the trails we could find hand-drawn by Inuit. And we found out, by using geospatial locating and putting them on this Google map, that they do indeed link up. So here's a network that visually shows you just how connected the peoples of the Arctic are. This map attracted a lot of interest from people in other parts of the Arctic, including the Sami and Greenland. And so picture these trails. It's not an exhaustive project. Going, you can see where at the top, where they cross over into Greenland over the sea ice, showing where migrations and travel have taken place back and forth. And then project them down across the west coast of Greenland, and you begin to see what connectivity really looks like. And for an up close, this is us working with elders on the maps. The elders have like this incredibly detailed knowledge. They point precisely where the camps are and where the trails go. And what's so good about working with them is they're reminiscing, often about their childhood, about trails that they learned when they were children, camps that they lived in. Some of them are only used once in a generation. Others they call the superhighways because everybody uses them all the time. So that gives you a little bit of a sense of the connection between the human societies and the physical landscapes that we're going to hear more about in a moment. Finally, emerging technologies. My point here is to say, well, television may be a relatively new technology and satellite technology, but actually Greenland had its own newspaper locally. You can see on the top left, Atuagaglitit, from the early 1860s. So there were printing presses up there. In the middle slide, sorry it's not so clear, you see the route of the transatlantic telegraph cable in the late 1850s, early 1860s, passing through Greenland. So it had this kind of geostrategic importance, right? And then on the right, you see these drawings by what's now appreciated, a really famous artist, Aaron of Kangak, which is around where Nuuk is, producing art that was then printed in Nuuk, again in the 1860s and 70s. And sometimes that's called the sort of Greenland Renaissance, because they were trying to reassert their identity in the face of this kind of long history of Danish colonialism. So that's in the 1870s. And that gives you really quite a good idea of both how creative the people are, how resilient, but also how long is this story of the search for self-determination. Okay. I think a collage or a montage is a good way just to illustrate the richness of a society, because we can only touch on it. And we see here from the National Museum of Greenland pictures of not kayaks, but umiak, the larger boat, to translate as a woman's boat for transporting family and so on. Sume, rock and roll band, lots of musicians coming out of Greenland. And further to the right, a recent film about cryolite that caused some ripples in Greenland and Denmark, looking at what Greenland has provided to Denmark and the rest of the world. But my point here is that there's a kind of cultural tapestry that's very rich, with artists playing an important role. Finally, what country can really be on the world stage today without playing football? Greenlanders are a little frustrated by not being able to play in the World Cup. The reason is they're part of the Kingdom of Denmark, and even though they're kind of neighbors, the Faroe Islands are recognized by UEFA. Greenland is not yet recognized by UEFA. So in their leisure time, they have a very active football league, as you can see. Okay. And that speaks to the question, are these people modern or are they traditional? Of course, you can have your cake and eat it. There's both. Finally, then, to sum up, what are the four kind of features or like themes I wanted to get across about research amidst the big picture of what's going on in Greenland? One, research partnerships. To think of these societies not as isolated up in the Arctic, but as highly connected societies, sophisticated with long histories and extended families. Thirdly, the colonial histories are essential to recognize in order to have any understanding of what dynamics are taking place today, more recently. And finally, understand that the real driving force is not necessarily about being an independent nation, but about seeking self-determination. That is to say, to have some kind of control of your destiny. Doing research in Greenland is a pleasure, and this was just a photograph I took on my way back to the hotel. Tying it all together, of course, Greenlanders in traditional mythology talk about football, talk about the Northern Lights, the Aurora Borealis, as the spirits playing a game of football with the head of a walrus. And you can decide whether in the photo you see the skull of a walrus and a game of football. Thank you for your attention.
Thank you so much, Michael, and thank you for setting the context of the peoples of Greenland and of the High Arctic, and of setting the context for both understanding their rich cultural heritage and where they are today, and how one might do research within that context. And so now we're going to turn to thinking about one of the pieces that many people think about when they first envision Greenland, which is a very large ice sheet sitting on the Greenland surface. And how is that ice sheet behaving and changing? And for that, we're going to turn to Kelly Hogan, who's going to tell us what's happening to Greenland's ice.
Yeah, thanks so much. That was really interesting to hear from Michael straight away. And I was also in Greenland before Christmas, and I was also at an all-party parliamentary group in Westminster last week talking about Greenland and hearing from a Danish minister. So we all know it's very high on everyone's agenda right now, but there are many, many reasons for us to think about Greenland. But And, this picture I put up to start with is perhaps a bit inflammatory, and I don't even need to be inflammatory. This is a picture from 2019 that people may have seen in the news of the high rates of melting that happen in the summer in Greenland on the ice today. This picture actually is on sea ice, and I won't talk about Arctic sea ice today. I'm going to talk about the Greenland ice sheet change, but we could come back to that later in questions if we need to. So it's pretty clear and a pretty obvious statement to say as our global temperatures increase, then we are losing ice in our polar regions. This is a compilation of essentially gravity data from NASA. They use satellites to produce it, and they look at mass loss, or how much weight of ice is being lost over Greenland over time. And if you look at the graph on the right-hand side, you could see that the mass being kept in the Greenland ice sheet, which covers about 80% of the land, is going down every year. You can also see a very clear sawtooth pattern there. That is basically because in the winter, then there's some snowfall, you make some new ice, and then in the summer, you get a lot more melting. But the trend overall is straight downward. So we are losing more and more ice from Greenland. You can also see, just as at the end of that animation there, that where we are losing ice from is at the edges of the ice sheet. So you can see that the biggest changes are the red and orangey colors. They're coming in now. This is ice that drains out through fast-flowing rivers of ice or outlet glaciers, and that drains out into the ocean. As you see, we're losing the most, obviously, from the edges of the ice sheet. So I just sort of talked about, that's sort of just the big picture story about how much ice, or the accelerating pattern of ice loss from Greenland. But how do we actually lose it? There's basically two different ways that we can lose ice from the ice sheet. One is, as I just talked about, is going out through the sides of the ice sheet into the ocean. And this is by the creation or the carving of icebergs that leave out through fjords and then get out into the wider global ocean. And that is a result of our warming that is happening to our oceans, and that is increasing the amount of iceberg carving directly into the sea. The second way that we can lose ice is to melt the ice sheet from the top down. This happens more straightforwardly as our atmosphere gets warmer. As the air temperatures increase, then you increase the amount of melting on the top, from the top down of the ice sheet. And then this water will flow off the sides, or flow down to the base of the ice, and eventually come out at the edges of the ice sheet as well. So Michael put up a timeline. So I'm a geologist, and so my timeline is a bit longer. And I think it's quite useful to just sort of hit upon some of the touch points for the Greenland ice sheet. Like, what do we know from studying it through time, its history through time, and what can we learn about what's going on in the future? So starting, sort of way back when. So we know that we've had a really large ice sheet on Greenland for the last 2.5 million years, the Quaternary period, more or less, and that it grows and shrinks according to the sort of standard glacial interglacial cycles on 100,000 year timeframes. If we jump forward to the last time we had a really big ice sheet on Greenland, that was the last glacial maximum. It's a little bit over 20,000 years ago, and we know that the ice grew out from its coastal position today. After that, when the climate started to get warmer again, the last time the climate was warmer than it is today was in a time period called the Holocene thermal maximum. And then we know that we actually had an ice sheet that was smaller than it is at present. And we know that from records of material that have been brought out from under the ice and pushed up into moraines. And if you take dates of those, then we know that the ice sheet actually got a lot smaller during that time frame. So then we're sort of compressing our time a little bit as we go into closer to now, and sort of the early 2000s or mid 2000s is right about when I started to study the polar regions. So like just as I was sort of a student in Cambridge and at the Scott Polar where I did my PhD, there had been the feeling was that the big ice sheets, Greenland and Antarctica, were sort of sleeping giants. It would take a very long time for anything to change them. They weren't terribly dynamic features. That is that was immediately turned on its head in the early 2000s. We saw big increases in surface melting in Greenland, big changes to the edges of the ice sheet. So those outlet glaciers that end in fjords were jumping back a huge amount. And it was a very exciting exciting time, not always in a good way, but also it changed the way that we think about the ice sheets, I think. Looking ahead a decade, we've had some very, very, very warm years through the 2010s, where every single part of the Greenland ice sheet on its surface had at least one day of melting through in the summertime, in 2010, 2012, 2019. This is a real change in the way that the ice behaves, and it affects many, many things. And then, looking forward, what happens next? It really depends on what we do with our emission scenarios with the greenhouse gases in the atmosphere. To make it a bit more exciting, I'll just sort of jump through what the ice looked like at each one of those time periods. On the left here, you can see, the last time we had a much, much bigger ice sheet, we had the ice grew out, sometimes several hundred kilometers from the coastline today, out to the outer edge of the continental shelf. It's a much bigger feature. And so you follow this red line or this black dashed line all around the ice sheet. Then, and I apologize for the fuzziness of this image, during that period that I talked about, the Holocene thermal maximum, when it's actually warmer than it is at present, so this is where we could be going in the future, we know the ice sheet was much smaller and much thinner. The dark red colors show where we've lost the most ice. The reason this is such a fuzzy picture is because this is really hard for models to actually work out and do a good job of getting this exact margin right. So they tend to put them in really small pictures so that they can hide lots of things. Looking more recently, this picture on your left here shows what these outlet glaciers that are jumping backwards and retreating from the coastline are doing. And you can see the blue colored circles are places where the ice has actually moved, has grown. And the reds, which is overwhelmingly almost all of the glaciers around Greenland, means that the ice is stepping backwards inland. And that is that warming ocean getting into fjords, melting ice, causing iceberg calving. For those of you who might know a bit about Greenland, we can look at one of the largest marine ending glaciers, Jakobtaven. Isbrae was its old name. It's called Cermek Kujalik in Greenlandic now. That's the name that we should be using. And you can see this pattern of sort of retreat from what was the Little Ice Age, a couple of hundred years ago. And then the ice margin was very stable in this sort of 1964 or 2000 position here. And then it was followed by, several kilometers jumping backwards in the following years in the 2000s. This is the beginning of a big period of change for a lot of the glaciers around Greenland. And it's linked to warm ocean waters getting in towards the ice and melting and carving icebergs. Where are we going with this? Well, it really depends on us. So if we run forecasting or predictive ice sheet models to look at what will happen in the future, it really depends on which emissions scenario pathway we choose. Things will take a while to change for, in a very big way for the ice sheet in terms of losing half of it or losing all of it. So it could be, several centuries to millennia before you lose everything. If you lost all the ice in Greenland, that is 7 meters of sea level rise, right? So what we do now, unfortunately, dictates which one of these pathways that we follow. So it only takes a couple of degrees of warming to start us on this trajectory. And we're at 1.2 degrees of warming over pre-industrial at the moment. So, this is what we need to find out more about. I can just run through a few sort of headline numbers just to sort of underline the point. So, the amount of ice that we're losing from our polar regions, basically from Antarctica and Greenland, is a staggering amount since the early 90s when we started to see this big pattern of change. From the 90s to today, in the 90s, it was only about 5% of the sea level contribution was from melting ice. Now it's 25%. So it's a growing component of the sea level rise budget. Most of that melt and that sea level rise has come from Greenland so far because things are changing there so rapidly. There is more ice and locked up in Antarctica, but it is a slower responder to the climate change we're seeing at present. And if you take this forward in predicted models, then you can see, we could get up to 27 centimeters of sea level rise from Greenland. That's at the worst case scenario with sort of the most risky sets of model runs. I had this compilation of sort of newspaper articles from about Greenland and Greenland ice loss. I made this last summer, and I didn't want to change it in light of the sort of recent flare-ups in the situations across the Arctic, because it's not just about sea level rise. It's not just about how much ice is lost. It actually impacts first and foremost the people living around Greenland. So if you start to lose the stability in the ice in the fjords, they lose their way of life in terms of hunting and fishing, and they are seeing that right now. They are struggling to feed their families, and so things affect them very quickly and a bit later for us, as the impacts are felt in the North Atlantic and the UK. I just want to lead on from that statement by saying that I think when I started studying this 20 years ago, sea level was the big driver. What was going to happen to sea level was the big driver. I'm sure people will have heard of tipping points or climate tipping points. This is a very big topic that people are very worried about now. And for Greenland, sea level is not the only thing that we need to think about. So fresh water coming from Greenland directly into the North Atlantic. I hope you can see my mouse up here. As that gets poured into the North Atlantic, it sort of puts a freshwater cap on the water in the North Atlantic Ocean, and that means that the overturning circulation that transports heat up and from the tropics to Western Europe and then back down, cold water back down towards the equator again, that circulation can be slowed down by that process. What the models say, our best models right now, say that the branches that feed into this from Greenland right now could weaken and slow down as early as the 2040s. That is not very far away, or 2050s. And then that the whole pattern of circulation, the AMOC circulation through here, could shut down in a couple of centuries. The implications for the UK would be incredibly large if that happened. We're talking about 10 degree cooler temperatures overall, increased precipitation. The amount of arable land across the UK goes down from 32% to 7%, something like that. The inability to grow crops of our own. So the implications are huge, and we do need to be worrying about this. Why does Greenland matter for this scenario? There are other sources of this fresh water from melting from rivers in the Arctic and from melting sea ice. But those are relatively easy to predict in terms of the physics as our temperature warms. Greenland ice and how it behaves going forwards, that is a much harder problem. That is the biggest source of uncertainty in these estimates. So that is why we need to focus on the ice sheet. I don't want to say much about this, but that is what we are trying to do with a really big project that has been funded by, people may have heard of the Advanced Research and Invention Agency. It's a UK government agency that is designed to allow scientists to progress some of these really big questions in a very quick way. This is a £15 million project, and it runs from taking observations with a lot of drones and autonomous vehicles right at Greenland's ice faces to get the physics right. What we are missing in the models is the physics of melting and calving. And in that way, we can't get how much fresh water will come to Greenland into the North Atlantic. And we don't know how good our predictions are on the timing of those tipping points. So I'll leave it there, but we can go back to any questions about Greenland ice afterwards. Hope that's okay, Jerome.
Brilliant. Thanks so much, Kelly. And thank you for setting the context of the Greenland ice sheet and how that's both affecting the people in Greenland and has changed in the past and may affect us going forward into the future. Now, I want to take a moment to remind everyone that if you've got questions for any of our speakers, please do put them in the chat. We're keeping a close eye on those questions, and we will return to those questions at the end. But now I want to turn to our last speaker, Owen Weller-Gibbs from Earth Sciences, to tell us a bit about Greenland's geological history and why critical minerals in Greenland is such a hot topic.
Well, hello to everyone across the world. It's great to see so many people engage with this topic. And I guess the subject of today's topic is why is Greenland so important? So as a geologist, it's probably no surprise I'm going to say the rocks. And specifically, I want to talk to you about some remarkable rocks from southern Greenland. So here we have a simplified geological map. There's 4 colors. In white, we have the permanent ice cap that Kelly's just talked about. In blue, we have the ocean. And the bit I'm interested in is the sort of the brown in between, which is the rocky coastline. And in particular, the red component, which is a major complex called the Garda igneous complex. And this stretches for several hundred kilometers across southern Greenland. And these are remarkable for a few reasons. So number one is that these rocks are around 1.1 billion years old. So we've had thousands of years from Michael, millions of years from Kelly, and now billions of years from me. And obviously, as geologists, we're comfortable with these numbers, but to help you sort of navigate these scales, I'm going to convert this into something you're more familiar with, which is the 24-hour Earth day. So if we take all of Earth history, 4,560 million years, and we map it onto a clock, then 1 second becomes 50,000 years and 1 minute becomes 3 million years. So with this scaling, we can say that these rocks in southern Greenland, these were created at just after 6 p.m. in the Earth evening. So again, for further context, the oldest rocks on Earth come from about 3 a.m. and the dinosaurs went extinct at around 21 minutes to midnight. And us humans, geologically, we've only been around for 4 seconds. But the reason I'm telling you this is just for context, because what's more important here is that at this time period, 1.1 billion years ago, or just after 6 p.m., southern Greenland was tectonically similar to the East African Rift at the present day. So this is a part of the world where the Earth's plates are actually beginning to separate. And if you pull apart the Earth's plates, you bring hot rocks from depth towards the surface, and this induces partial melting. And at the surface, we see volcanoes as an expression of this, such as this beautiful photo here. But what's important for us as geologists is what's happening underneath those volcanoes. So if we now look at a cross-section through the crust, then that's what's shown here. So this is going down into the Earth's crust. We can see the volcano at the top, but volcanoes are fed by a series of magma chambers. And this is magma that's moving its way up through the crust because it's positively buoyant. And as it moves up through the crust, it cools, it produces crystals, and these crystals settle out, and the magma composition slowly changes as you move up, which is a point I'll return to later on. Now, obviously, this was what Greenland looked like 1.1 billion years ago. We've since had 1 billion years of erosion, and that's basically wiped away this top layer. And so we're now looking at an erosion surface, which is within these magma chambers, which are essentially fossilized or frozen. So when we're walking around the Greenlandic landscape, like this field photo, this is what you see. And you can see it's a bit of a paradise for a geologist because it's almost 100% bare rock. And in the background to this photo, hopefully you can see that there are layers dipping off to the left-hand side. And these are not sedimentary rocks, but these are igneous rocks. And the layers here, again, crystals falling out of these large magma chambers. So we've got these wonderful 3-dimensional frozen magma chambers, which we can go and study the processes that are going on inside them. Now, if you go to these particular outcrops, there are 2 particularly amazing features which are particular to southern Greenland. So first of all, if you look at these rocks up close, so you can see my scale card there with centimeters, then what I'm doing to this rock is I'm shining a UV torch, just like this little torch here, onto this outcrop, and the UV torch is creating a fluorescent response in one particular mineral here. So that mineral that's glowing orange is a mineral called sodalite. These are relatively rare on Earth, but you can see in this particular outcrop, this rock has got almost 50% fluorescent sodalite. So if I moved my torch around, then different parts of this would glow orange. So it's interesting. It's full of this unique mineral. There are also other unique minerals, and of particular interest to today's talk and in the news is this red mineral here, which is called eudialyte. So I'm not expecting you'll have heard of this mineral, but the important thing is that within this structure of this mineral is it contains abundant rare earth elements, which have been all over the news over the past few years. So just to remind you what rare earth elements are, here we have a periodic table, and shaded in turquoise, we have the rare earth elements. There are 17 of them. So at the top there, we have scandium and yttrium with the SC and the Y. And then the star shows you the 15 lanthanide elements, which stretch from lanthanum to lutetium. So rare is something of a misnomer. So the most abundant rare earth element is cerium, and that's got a similar concentration in the crust to copper. And we don't think of copper as particularly rare. Even the most or the least abundant rare earth elements, so thulium and lutetium, these are still 200 times more common than gold in the Earth's crust, so they're really not rare things. And if you're interested in trivia or you're trying to remember the name of these different rare earth elements, you might think they all sound quite similar. Then my recommendation to you is to remember the name of the village where hosted the mine where many of these elements were first discovered. So this village was called Ytterby in Sweden, and because of these different rare earth elements, they named 4 of them after Ytterby. So we have yttrium, terbium, erbium, and ytterbium, so all quite similar. Thankfully, they didn't try to name all 17 after this village, but sticking with the Scandinavian theme, they also then had scandium for Scandinavia, holmium as a nod to Stockholm, the capital, and thulium, which is a mythical term for Scandinavia. So I'm telling you this not just to help you with the next pub quiz, but also because this tells you that the rare earth elements commonly come as a set. So it's rare that you'll ever find them concentrated, and you'll never find them as sort of separate elements, but rather they come within minerals all as one group and one set. And the reason they've been in the news so much recently is because for many countries, they're considered a type of critical raw material. So being a critical raw material is a time and spatial dependent concept. So this is a graph which the UK government produced in 2024. They took roughly 80 materials, and then they scored them based on how risky their supply was, like how few suppliers there were, and what is the economic importance of that material to, in this case, the UK. And if they score relatively highly in both of these categories, they fall into the turquoise part of this graph. And that defines that mineral or that material as being critical. And you can see the rare earth elements in orange here, they score highly both on supply and economic importance. So on the supply side, there are relatively few countries producing, it's mainly China, and China also absolutely dominates the production side or the processing side. And then in terms of economic importance, rare earth elements are used in a whole range of modern technologies. And most importantly, and again, speaking to sort of Kelly's talk as well, the rare earth elements are going to be critical for the green transition. So if we want to reduce carbon dioxide emissions, we need to build an awful lot more wind turbines, for example. And within wind turbines, we have each wind turbine over 1,000 kilograms of rare earth element. And the reason we have them is because of their spectacular magnetic properties. So here we have a graphic showing the strength of a rare earth magnet on the left. Don't worry about the units. And on the right, we have a sort of typical normal sort of ferrite magnet, the kind of magnet you'd use in your fridge. And you can see that for the same mass, rare earth magnets are over 10 times as strong. And it's this property, which is one of their most important properties. And it just means we can make technology lighter and stronger. So it happens that over the last year, we've been developing a museum exhibition exactly on this theme. So if you're interested in this topic, then please do come along. It's opening in the Sedgwick Museum of Earth Sciences. It's called From Magma to Magnets, and hopefully you can follow that link now. And I'm really excited to be sharing this with you because if you come along, you'll get a sense of some of the things I've talked about. So if you wave your hand at this orange handprint here, you'll turn on a UV torch and you'll be able to see minerals glow for yourself, just like we do in the field. And we've also got a wheel external to this case, and you can turn the wheel and you can feel the strength of a rare earth magnet versus a normal ferrite magnet. So you'll be able to sort of bring to life some of the topics that I've talked about today. And this opens in February half term, and it will be open for the foreseeable. So if you're not based in Cambridge, then I'm sure there's a good chance of being able to see this. Okay, so I just want to tell you a couple of things about the actual science that we're doing in this space before finishing with a few field photos from Greenland. So there are many questions that we're trying to answer with our research. And one of the most fundamental ones is what controls the extraordinary diversity that we see in these complexes? So on the left here, we have a geological map of Greenland. Each color is a different kind of rock type. And on the right, we have a classification diagram, which is showing you something about the composition of these rocks. So up the y-axis, we have the total alkali or sodium and potassium content. And on the x-axis, we have something about how much silica is in the rock. So the details don't matter, but by plotting up the rock compositions on this kind of diagram, we can begin to classify rocks into different rock types. And so the green rocks are rocks we call gabbros, the blues are cyanites, and the oranges are granites. And on the map on the left, you can see that all three of these rock types, and these are extremely different chemically, are located in a very proximal locations. And so one of the big questions is why do we see such extraordinary diversity? And so in Cambridge, we've been developing new thermodynamic computer models to help explain what happens to magma as it moves its way up through the crust. And one of the results for our modeling was to show that we can explain all of this diversity from if you take the green rocks, the gabbros, and as they move their way out through the crust, if they're able to incorporate some of the local crust into the magma, then you evolve from being the blue rocks to essentially along the pink line and into the orange rocks. And we've been able to show that if you incorporate around 15% by mass, then you can beautifully explain all of the observed rock types we have here. So we can begin to rationalize and understand all of these compositions. So it's not just incorporating the crust by melting it that's important, but in a separate study, we've also shown that the pressure that these magmas reach is also really important. So just like Kelly had a tipping point, here we've got a tipping point, which is that purple layer. And this is a layer within the mid-crust, so around 10 kilometers into the Earth's crust. And if magma stalls just below that point and it crystallizes, it's on a journey to becoming those blue rocks, the cyanites. Whereas if that magma goes slightly shallower into the crust, it will evolve along a trajectory to a rock you're probably more familiar with, granite. So again, the details aren't particularly important, except to say that we can begin to understand the important processes that control this diversity. So things like assimilation and pressure. And we can also actually quantify what's the best composition in order to have the most rare elements. And this star just shows you where an ideal magma would end up, and it would be just below this mid-crustal tipping point. And that's when your magma would become the most enriched in rare earth elements. So by doing this work, hopefully we can help to guide future research for more deposits, as we'll certainly need more of these elements for the green transition and electric vehicles and so on. So this research is ongoing. And so we're currently planning our next field season in Greenland. And people always ask me, how do we get around? How do we do field work? And this is a picture of how we get to our field sites. So we employ local sailors and we rely on their skills to navigate these iceberg-strewn fjords. And then we're dropped off at different campsites. And here you can see some of my fantastic team. And inside those plastic tubs, we have long life food. And the challenge for us is we have to eat food fast enough to then replace the food we've eaten by the rocks that we collect, because we take out the food, replace it with rocks, and then ship the rocks back to Cambridge. So the next thing we do is we set up camp. This was our favorite campsite from our last field season, with this beautiful view across the icebergs. And it's amazing to see and appreciate how dynamic these icebergs are in terms of how they break up and crackle. And we sort of named these all like clouds to entertain ourselves over dinner. And then from this campsite, we head off into the hills to look at the rocks. And as the others have suggested, the views are fantastic. As a geologist, we try not to get too distracted by the views, and instead we really focus on the rocks and try and understand what they're telling us about the magma chambers. So I was lucky enough to be an undergraduate at the Earth Science department here, and it's great to be able to use all the skills I learned and all the field trips into practice, because as good as our computer models are, we have to be guided by the principles and things we observe in the field. And so with that, I'd just like to finish by, again, just acknowledging the great team that I work with, both within Cambridge and in Greenland and across the world. So here we have postdoctoral researchers Carrie Soderman, and on the right, we have Charlie Beard, who's now a lecturer in critical metals at Utrecht University. And with that, I'll take any questions. Thank you.
Great. Thank you so much, Owen. And thank you for giving us a sense of where these critical minerals come from, how they're sourced, and why the study of them is such a rich and complex history to pull out of such an old part of the planet. So we've got lots of questions coming in. Please do keep those questions coming. Of course, we won't be able to answer all of them, but we're going to try and select a few from amongst the questions that have come in and that are continuing to come in. And certainly, I know that all of our speakers really enjoy and appreciate the kinds of questions and engagement that they get from the general public and certainly within this webinar. But let me start by sending one question to Michael. So we have a question which is, where does the word Greenland come from? And I wonder if I can tie that into a second question, which is really asking about the cultural links between the Greenlandic peoples now in Greenland and Denmark.
Thanks, Jerome. They link in an interesting way. Kalalet Nunat, the Greenland have their own name for their country, which means really the land of the people. And what that tells us actually is how important language is. So the question about where does Greenland come from, there are different theories. One is that back in the day, they got the names of Iceland and Greenland confused and reversed. Another slightly more compelling theory is that Eric the Red, going back 1,000 years, was a kind of marketing ploy, wanted people to come and settle in Greenland, and that maybe informed the name Greenland. So that's kind of the, I guess, how we ended up with Greenland. Question about relationships, is that right, between
Yep.
Greenland and Denmark? Think of it, and I don't say this tongue in cheek, but in a difficult, complicated relationship, a difficult marriage. And so I don't want to trivialize it. It's really important. When you have such a long history of colonial relations, on the one hand, Danish leaders will rightly say they are very proud of the contribution of Greenland to Denmark. They want to support Greenland's aspirations for self-determination and eventual move towards independence. The Greenlandic, so the Danish position is to support that. Greenland also has its own representation, very experienced diplomats in Washington, D.C. for many years, in Brussels and so on. But many Greenlanders feel that their culture and language is not well understood. Not many Danes speak Greenlandic unless they have lived in Greenland a long time and possibly married into Greenlandic society. So there's a very entangled relationship. And that makes the need or the desire for self-determination quite a complicated one. If you ask many Greenlanders how they feel about Denmark's attitude towards them, they will use phrases like tone deaf. So that captures something about how complicated these dynamics can be.
Wonderful. Thank you very much, Michael. Now, we've also had a number of questions about the ice. And of course, Kelly has highlighted how both within its glacial history, the ice sheet has varied, but now due to our emissions, the ice sheet is declining rapidly. Well, there's a question about what happens to the land surface after you deglaciate. Kelly, do you want to say something about what happens to the land surface? And we have a question which I'm going to paraphrase around erosion as that glacier retreats.
Yeah, sure. I mean, some people may have heard of the term post-glacial rebound. So if you remove ice or you lose ice into the ocean, then you're removing that weight of ice from the land. So what happens is that the land slowly will pop back up as that weight is lifted off or transferred elsewhere. We still see the effects of post-glacial rebound from the last glacial in the UK. So Scotland is still, the northern part of Scotland is still rising by several centimeters a year. And because the UK is sort of long and skinny this way, they are rising in the north, and that actually tilts us in the south down. So as much as Scotland is rising, the southern corners of England are actually sinking relative to a midpoint in the middle. So those effects of post-glacial rebound are taken into account in models that predict ice sheet loss. So if you lose ice from somewhere, then the land does adjust for that in the models that we have. There are some uncertainties still remaining, particularly about how viscous or how viscous the mantle is, so how quickly it will pop back up. We don't know that really well for everywhere. So what that means, if you think about then sea level rise going forwards, is that you have to think, I just talked in global sea level rise, terms of global sea level rise. But if you want to know for your place on the planet, what's going to happen, you have to think about the local effects. So it would be different in Scotland than it is in London. And similarly, it'd be different, in the Southern Hemisphere. The other player in that story is gravity. So where there is already a lot of weight on the Earth's crust, the response or the sea level moves around in different places on the globe. So unfortunately, places like the Pacific Islands, who will feel not only are low lying and will feel sea level rise first, they also are affected by that lack of gravity there, which means that actually sea level rises faster there than it will for other places on the planet. So it's not a fair system.
Thanks very much, Kelly. Of course, we also have lots of questions which are really around the mining and the built infrastructure, and thinking about how realistic is it to get these rare earth elements out of Greenland. And I know that, Owen, you've spent a fair amount of time doing fieldwork in Greenland, and so know something about the challenges of operating in that environment. Can you say something about mining and or operating within the Greenlandic environment in the field?
Sure. So yeah, obviously, as you would expect, we could only visit Greenland for fieldwork with sort of limited seasons through the summer, particularly late summer, because early summer you get a lot of sea ice coming down and that can block the fjords. So yeah, it's a very challenging place to be for sort of 10 months of the year. For 2 months of the year, it's fairly glorious if you're away from all of the black flies and the mosquitoes that want to eat you, and if there are no polar bears around. But yeah, it is a difficult place to be in winter. There are certainly abundant rare earth element resources in southern Greenland. There's a lot of mining companies which are doing exploration in the area. There's lots of permitting processes, and there are actually historical mines. So in southern Greenland, they used to mine for uranium and particularly thorium. And that very same mine and that same mineral is now being looked at for rare earth elements as it has both. But that tells you the difficulty of mining in southern Greenland, because the minerals which contain the rare earths also have this radioactive waste component. And so understandably, there is local concerns and obviously some opposition, and it needs to be handled quite sensibly as to how to go about that. But the estimates are that there's actually the third and the fourth largest rare earth element deposit in the world in southern Greenland. And I kind of alluded to it a little bit in the talk, the main challenge with mining is not so much extracting the rocks, that will be feasible even in inclement weather. It's actually processing the minerals themselves. The Greenlandic rare earth minerals are very long formulae and quite hard to crack. So for the foreseeable future, until people get better at processing that particular mineral, I don't think it's going to be viable moving forward. But potentially it is the world's third and fourth largest deposit.
Brilliant. Thank you, Owen. All right, we are barely with any time left, but I do want to sort of give all of you the impression of how this kind of science gets fed into the UK government. So Kelly, with only a few seconds left on the clock, can you say a little bit about how the British Antarctic Survey, as an example, feeds its critical science into UK government decisions?
Yes, briefly, there are 3 ways that we do this mainly. So we feed into policy documents. So these are sort of documents about the state of the cryosphere or the state of the polar regions that go through things like the Intergovernmental Panel on Climate Change. These are the big reports that have these numbers about sea level rise and ice change. Then we go directly to the UK government through all-party parliamentary groups or direct briefings when they solicit those. And then we work through our funders to feed back those messages. But I would say there's a choke point that the messages don't always get through.
Thank you, Kelly. And as you've probably understood from these 3 excellent talks, a huge part of doing this research and a huge part of the excitement is communicating it not just with the UK government and not just with other scientists, but really having that conversation with you and the public. And so thank you very much for all of your questions joining us today and hearing about this research in Greenland. And a huge thanks to Michael Bravo, Kelly Hogan, and Owen Weller-Gibbs for sharing their research and a little bit of an insight into why is Greenland so important today. Thank you very much.